Thank you very much, everyone, and thank you for inviting me to give this talk. So yeah, I will talk about the challenges and the stakes about monitoring the carbon, and I will focus on one example, which is arable land, to explain you more what are the challenges. So. Well, it started with the 4 per mil, of course, and the idea that we should store more carbon in the soil for climate issues, but also for more sustainable production, soil fertility. The question was, how can we store carbon, where, at which price? So we started, INRAE started a national expertise, or coordinated a national expertise that was published in 2019. And this expertise was based on some crop modeling with sticks, for instance, using a 1 kilometer grid in which we estimated what was the main crop rotations, and there were some assumptions or based on national statistics of different practices that were implemented, and then different scenarios were tested, and among those different scenarios that were tested, one of them was increasing the amount, the frequency of the cover crops and their duration in order to test how much carbon that would allow to be stored in the soil. So on the left, that was the reference scenario that I helped building based on the AgRest statistics that were a little bit old, and we estimated then that depending on this or that kind of crop rotation, allowing X number of months of fallow period, then we could insert or not additional cover crops. So it resulted in several numbers that I will not necessarily recall now, but showing that there was a significant potential for storing carbon, and a large share of that was allowed by cover crops, and it was mainly on arable land that are quite depleted in carbon, that we could store more carbon. But actually, the reality is a bit more complex than that. We actually don't really know where we are in the landscape, if we are more here or there. We don't have actually database that information that allows us to know where cover crop agroforestry is implemented, what is the quality of those carbon farming practices that are implemented. For instance, if cover crops are well established, well developed, and what is the true carbon effect of those carbon farming practices, and that's a big problem. So based on that, we realized that we need to assess the real impact of those carbon farming practices in terms of CO2 emissions, carbon storage, at plot scale, but over large areas, to know really what's happening there. And that led us to develop a new generation of tools, providing a more objective, exhaustive vision of the effect of those management practices on soil carbon stock changes, and that would be adapted to different contexts of monitoring. And so that links well with the previous presentation. So just want to remind that it's not only about the voluntary carbon market. We want to monitor carbon stocks also in the context of the national inventories for the carbon offset and insetting, of course. And we would like to do it also for the common agricultural policy, but we currently don't have the tools to do that, because that means we have to be able to monitor for each year, each plot, all over our country, how much carbon has been stored by a farmer. And what is important to keep in mind also is that each of those contexts of application has its specificities, requirements, rules. For instance, the insetting we were talking about. We'll take the example of a company we are working with that is producing popcorn, the Nathalie company, and they are contracting with the farmers for 1 year, 1 plot, and they want to know how much carbon has been stored on that plot that year, because that's the year when the farmer is producing popcorn maize for them. It means that we need a tool that is able to assess what they pay is actually how much carbon is stored with cover crops. So we need to know how much carbon has been stored with the cover crops on that field that year. While with the voluntary carbon market, you need an assessment on 5 year, 10 years period. So you need other approaches. And with the cap, you need an annual approach, plot scale also. So different requirements and rules. And just to give an example, show an example of for the voluntary carbon market, there are some approaches that are measure only, model only, hybrid. Some are practice based. So it's a bit of a mess, in fact, and we will try to have some more harmonization on those methodologies. That's what I will present later on. But first, let's keep in mind how to measure carbon in the soil. So there are some measure and remeasure approach. So we want to quantify the soil organic carbon content and the bulk density in order to be able to calculate the stock. We can use this information for the voluntary carbon market, as I was showing on the previous slide, or for national inventories, for instance. But if we want to do that for the voluntary carbon market, I mean, it will represent a huge number of samples. If you want to detect the effect of a cover crop, it's about 25, 75 samples per hectare. I mean, so it will be super expensive. There are some risks also of uncertainty, lack of representativity of the where there is some carbon stored in the farm. Well, many other issues that some of the new techniques like gamma ray and NIRS might solve, but anyway, I mean, if we analyze the number of magnitude, if we just consider the number of plots in France, and considering that we only take 3 samples for the measure and 3 samples for the remeasure, and at a price of 50 euro per analyzed, is considering the time and the effort to go to the field and then to analyze the samples. I mean, that's a reasonable price. I mean, that would be how much we would have to pay just for remeasure, and that's how much money we get for the whole cap. So it's just nonsense. We cannot do it this way. So there are some other approaches that are used, statistical models specializing in situ soil data, but that's mostly used for national inventories or for global products like the soil grids. There are some tier 1 and 2 approaches that are estimated standard values of carbon storage or release based on specific land management measures, mostly used for national inventories. Very often we hear that remote sensing could be useful to monitor directly carbon stock or carbon stock changes. So this is a study from Emmanuel Vaudour, but actually we don't know what is the real soil carbon profile. Is it increasing or decreasing compared to what we observe at the surface? Well, in fact, we cannot use this approach because we only see the surface and we don't have any idea of how much is it representative deeper in the soil. So let's forget about this one. And process-based modeling, maybe we can come back to that later on, but I say for the moment, let's forget about this one. And and then, of course, there are process-based modeling, tier 3 approaches. And I will have a focus on that today, but basically the idea of those process-based modeling is to quantify all the carbon that is entering and leaving the plot, and it means that without maybe knowing it or being conscious of it, you're using a carbon balance approach that you can use also on the field to calculate carbon budget with flux tower setups, for instance. But basically, you want to calculate how much carbon has been stored in the soil or released by considering all the CO2 fluxes entering, leaving the plot, how much carbon is exported at harvest, and eventually how much carbon is brought as organic amendments. And you have a dynamic vision of the carbon stock with that. Thing is that so monitoring soil carbon, in fact, is not a soil issue only. It's an ecosystem issue. You need to know how much CO2 is entering the plant, how much biomass is there, how much biomass goes to the soil, etc., etc. And then the methodology, those methodology will depend on which context, availability of data, accuracy of data, cost accuracy issues you are in. So this report from the last year from the United Nations explain that the main challenge concerning for the promotion of carbon farming was in fact related to the monitoring of soil carbon sequestration, and mainly related to issues of scalability of the MRV methods, monitoring, reporting, verification methods, and the ease of using those MRV tools. Actually, Ceschia gave some recommendations at the end of the project that we should use some modular and transparent approaches with some uncertainty assessment, recommending to use several soil models instead of one in order to be able to do ensemble approaches. Well, they gave a number of criteria, including the fact that we should use remote sensing to quantify more accurately how much carbon goes into the soil. And this should be compliant with the current EU CRCF concerning the baseline, the assessment at plot scale, what are the practices accounted for, and considering the quality criteria that you have just presented. So, in order to achieve that, there were some frameworks, conceptual frameworks that were proposed by Smith et al. And by Postian et al. That were in fact giving us the ingredients. You need some soil measurements, you need some models, you need some remote sensing, but not really explaining how to use those different ingredients to make a recipe. So since then, there are some prototypes of scalable quantification platforms, Keith Postian calls them. I will present in detail this one later on, that are trying to make this approach more operational. Before we get there, we need to have some more harmonized approach of how to monitor, report and verify soil organic carbon stock changes. So that's a framework that we have proposed in our CASA that is describing in this box the different monitoring methods, in this box the verification and reporting, and how to assemble different bricks, the remote sensing, the modeling, the different modeling approaches in order to make this system work. So I won't describe that now in detail, but I will show you some examples. And I will focus first on one approach that is probably the one some of you know the best, which is the soil-centered approach, so process-based modeling focusing on soil. And this is typically what we are using in the label bioCarbon with the AMG model, which is a very simple soil model. The pointer laser is dead again. And as input, you need to providing climatic data, soil property data, how much biomass goes into the soil as crop, and for this you would rely on the yield data provided by the farmer. And the more difficult problematic thing is for cover crops, because you have to provide a number to AMG, how much carbon goes into the soil as cover crops, and the label bioCarbon methodology tells you that, well, you can rely on regional statistics, for instance. You can do some in-situ measurements, but without giving real protocols on how to do that well. You could use remote sensing, but at this time there was no remote sensing approach allowing to do that. And the problem is that all this is very spatially variable. And that's just an example of superficial soil organic carbon content, spatial variability near Toulouse. And if you give those numbers with some uncertainty to the model, then you will have higher uncertainty as an output, garbage in, garbage out. And as a matter of fact, when you look at the spatial variability in the biomass for wheat, this is at French level, something we did with the AgriCarboN processing chain, you see that there are some national, some gradients or spatial variability at national scale, at landscape scale, but even intra-plot scale. And when you look at the harvest index that is recommended to be used to estimate how much above ground biomass is produced based on the yield data provided by the farmer. I mean, just for wheat, it goes from 0.3 to 0.61, in fact. So, wow. That's a lot of uncertainty. Just a map to show you for grain how much it is spatially viable inside the plot. So using this approach causes a lot of uncertainty in the carbon inputs to the soil model. And for the cover crops, it's the same. I mean, we're talking about using eventually regional statistics, but only near Toulouse, for the same cover crop species, favabine, we see that there is a factor 10 from one plot to the other when we ask the operators to go in the field and take a sample that they think is more representative of the field, which means we do not cover the spatial variability inside the plot. And the reality is this one. This is a plot that has been sown with cover crops, and the red areas are where the cover crops have actually developed. So if you consider that because you have some cover crops here, you will have a homogeneous cover, I mean, that's not what happens. So we better use some Earth observation to quantify or be more objectify and quantify more accurately all those practices actually are implemented and how much biomass they produce and put into the soil. So if I analyze a tool like AMG, there are some pros and cons. It's very easy to use. It simulates most of the crop and carbon farming practices, but it's simulating things at a cropping system level, not at a plot level, meaning that you cannot even verify the results of the model. The cost may be quite high if you have to initialize the soil with in-situ soil measurements. There are no uncertainty assessments. It's not very scalable. And as I was saying, you cannot do any verification with this approach based on measure-remeasure. So if we test another approach, which is an ecosystem model like sticks, you need a lot of input data on management. It's a rather complex model, so you need many crop parameters. And the outputs will be homogeneous at plot scale, meaning that, I quicken a little bit because I see the time running. In short, you need a good expertise. Most crops and carbon farming practices are modeled, but there are no uncertainty assessment. Where to verify the outputs? I mean, where to sample? How many samples do you need to have an average soil sample at plot scale that is representative of your field? And the main issue is that you need to collect many activity data, sowing density, sowing fertilization input, which time, how much, etc. So it's very time consuming and very costly. And you don't have a good representation, of how much biomass. Oops, sorry. And you. It's tricky. Laser pointer. You have a homogeneous estimate of biomass, while in fact there is some strong spatial heterogeneity, including inside the plot. So, in order to reduce or improve this, some have assimilated remote sensing data in models like sticks to better represent the spatial variability intra and interplot of biomass production and carbon inputs to the soil, but still you are limited by the fact that you need a lot of activity data to be collected and that it's very costly and there is a lot of uncertainty associated to those activity data. That's why there was a new approach developed in my team based on the limits, on the analysis of the limits of the current methods. I will not talk about artificial intelligence now, but if you want, we can discuss that afterwards. So the approach is a parsimonious approach, what we say. It means that we try to get the right level of complexity for what we want to do, which is monitoring soil carbon at large scale and high resolution. So it's combining observation, data assimilation through a process that we call basalt in the CESBIO crop model that simulates a certain number of variables, and the biomass produced is used as the input for the IMG soil model. And we have a strong focus in this approach on the effect of the biomass inputs to the soil on the soil carbon stock changes. That's how it looks like. It's an automated processing chain that automatically downloads the data, remote sensing data, soil data, climatic data, etc. Once you give him a map, it will automatically download the data, produce some time series of leaf area index with their uncertainties that are then assimilated in the crop model, providing carbon inputs to AMG, and then we are producing some maps with their uncertainties. And it's based on this model, the CESBIO model, that was really built for upscaling. It means that we do not represent all the processes as in a model like STIX or CERES, but we force the model to reproduce what is seen by remote sensing. And by doing that, we force the model to reproduce, to take into account implicitly for some carbon farming practices, for some stress effect, and it produces more realistic estimates of the CO2, water fluxes, biomass yield, that we validate independently with different data sets like flux tower measurements, like in situ biomass, in situ yield measurements. Carbon budget assessment can be done based on soil sampling, of course, but so far we did it only on based on carbon budgets calculated with flux towers, simply because there are no measure and remeasure data sets since the Sentinel-2 satellites were launched in 2017. And we need very, very little activity data, only the ones related to straw management and organic amendments in order to calculate the carbon stock changes, but not for the other variables. And the last thing is that it allows automatic detection of cover crops, spontaneous regrowth, and weeds that affect the carbon stocks and that are never considered, accounted for, while they really have an effect, as we showed in the former paper. Well, it allows to produce some nice maps of the CO2 fluxes, annual CO2 fluxes, of the carbon exported at harvest, of the carbon budget. You have the distribution in this area near Toulouse that is 110 by 110 kilometers of those different variables, as well as their uncertainty. And you see here for straw cereals that we are storing carbon on average around 100 gram carbon per square meter, but there is a rather high uncertainty on this number. And we can produce map now at national scales, meaning that this approach can be used for national inventories or for the common agricultural policy. So far, we didn't have tools that would allow us to have a national scale vision of the carbon budget components, and it can be used to compare the effect of, for instance, having cover crops before maize or not. And in this exercise, we simulated first reality, which is a cover crop before maize. And here we voluntarily neglected the presence of the cover crops, and by calculating the difference between the two simulations, we see the effect of cover crops on carbon storage. And we can also test some scenario, like what would be the effect of incorporating all the straw or exporting them on the carbon stock changes at an annual time scale. This is therefore a diagnostic approach because it's based on what the satellite sees, but it allows to test some scenario, and it can be used to produce some high-resolution carbon budget maps Here it's the Natais farm where they're producing, where the CEO of Natais owns. And you see that it's very green in the landscape. It's because here they have a maize, wheat crop rotation, and each year before the maize they have a cover crop. So it means compared to the other farmers, they are storing much more carbon because there is a cover crop every second year. And you see some special patterns here. Here it's losing more carbon because of the kind of crop rotations that they have, and also the influence of the Mediterranean climate, which is warmer. Well, I could explain you some those patterns, but what we can achieve with that in the end is that you can analyze for each line is one plot, and you can analyze the trajectory of each plot. Here it's for maize wheat crop rotation, depending on how many cover crops are there during the crop rotation of 5 years. And you see that the more you have cover crops and the more you store carbon. And for the ones that have no cover crop at all, they are close to equilibrium. And we can do that for all the crop rotations, meaning that we can have some kind of combination of a plot-specific baseline that is needed to calculate the carbon stock change, and something that is close also to a regional baseline that is mandatory for the CRCF methodology, meaning that it's compliant for different contexts of application. And some implications for the verification process of using this kind of approach compared to AMG or a classical agronomical model. When you produce with FairCarboN the maps of the crops and cover crops and their certainty, and use that as an input in AMG, then you can produce those annual carbon budget maps, as I showed you before. And you see here the plots that are in yellow, orange were on winter wheat that year, and they were close to neutrality, losing a little bit of carbon, while the ones in maize preceded by cover crops are all in green, and they were storing carbon. But what is interesting to look at is that inside a given plot, you have some areas that are losing carbon and areas that are storing carbon. And if you have this dynamic vision year after year, you can use this information to define an optimal soil sampling scheme that will allow you to monitor the areas that have a strong positive and strong negative carbon dynamics, meaning that you will detect faster the carbon stock changes, but also the fact that you have this vision at a farm scale reduces considerably the number of samples you have to take in order to have a representative estimate of the carbon stock change at the plot or farm scale, which reduces considerably the cost for verification compared to the other approaches. So, pro and cons of this methodology. Well, the main con is that you better be quite good in programming, because it's in Python, and it has been developed by some geeks in my lab. But the idea is to integrate that, in fact, in some already existing platforms, like, for instance, Carbon Extract. So it will that's why you don't need a front end, in fact, because it will be included in already existing technologies. Another big limitation is that right now we are mostly monitoring the main crops and the main cover crops, and we have a lot of work to do to include more crop species, cover crop species, so we can actually use that more in a personal way. The good things are that it's simulating at pixel level, meaning that you can really go in the field and validate your model based on the biomass component, the yield component, the soil organic carbon stock changes. You can measure that on the 20 by 20 meter area as they are doing for the RMQS. You are the same scale. You can really validate your model at the scale of simulation on all those different carbon budget components. The cost, well, it's mainly driven by the cost of collecting the activity data, in fact, because you can produce, I didn't say, the map at French scale, it was one day of calculation on the CNES supercomputer. So the cost of producing the information at high resolution, very large scale is super low. But so mainly the cost is related to collection of activity data and for the soil sampling, which is reduced compared to the other approaches for initialization, but also for verification. The scalability is very good. I mean, it has been built for that. We still have some limits because in very cloudy conditions or long cloudy conditions, the system might not be operational. That's why we are about to include some radar satellite measurements that are insensitive to cloud coverage to make it operational even during a long period of clouds. You have uncertainty assessment because it's a Bayesian approach that propagates uncertainty till the carbon budget maps. And the accuracy will depend a lot on the quality of the local soil data and of the quality of the activity data, but that's true for all the modeling approaches. And one of the big pro is that the same approach can be used for the different contexts of application, meaning that the numbers that you would produce for the cap would be the same as the one you would produce for the in-setting or for the voluntary carbon market or for the NDCs, meaning that you have some coherence between the different contexts of monitoring. And the big challenge is really to have the access to those reliable management data. And often we are said that, oh, but if you just collect activity data based on with some APIs from farm management information systems, that will solve the problem. Well, no, because you really need someone like in the agricultural council or in the cooperatives, technicians that will look at the data of the farmer, make sure they are consistent. Last time we tried to do that with the agricultural council near Toulouse, there were 3 sowing dates for the same plot for the same cover crops. So, because anyway, this solution will not solve all our problems, because there will be some situations when we cannot use that simply because the plots are too small, or because there are some trees in the middle with agroforestry systems, or because there is too much slope, etc. We will need to combine, in fact, those different modeling approaches, like MJ with FairCarboN in other situations, and in order to choose the best method to implement depending on the context, meaning if it's for the NDC, for the CAP, for the voluntary carbon market, and depending on the local conditions, we need some kind of decision tree. So that's what we built in Orcasa, and it will be available at the end of the year. And I know who's here in PG with me in the room. We prepare a paper to present this MRV framework and decision tree. And to conclude, 0-0. Yeah, as pointed out by Orcasa and Circasa, we needed to develop new monitoring methods and a consistent framework for MRV of surrogate carbon stock changes for those different contexts of monitoring. And based on this observation, and after analyzing the different pros and cons of the existing approaches, including Tier 3 approaches, we started developing the FairCarboN processing chain to match as closely as possible the recommendations of the Circasa deliverable. And now we produce a system that is pre-operational, largely automated, enabling dynamic and more objective assessment of the effect of biomass input entering the soil on carbon stock changes. There are still improvements needed. I won't get into details, like adding more crops, etc., to make it more operational. And also, it's not it's not a one fit for all solutions, as I was explaining just before, because we will not be able to use this approach everywhere all the time. So we need some decision tree to guide us on what is the best approach for monitoring carbon stock changes. And 2 challenges that are common to all the modeling approaches is that we have to reduce the uncertainty on the soil properties, on the initial soil organic carbon stocks, and then on the stability of the carbon for reducing the uncertainty of the model's outputs, and that's why we start working with Pierre on including the Roqueval approach in FairCarboN, for instance. And the big problem is really accessibility to reliable activity data, especially when we want to apply those methodologies at large scale, like for the CAP. So thanks a lot for your attention.